This next reaction is called the Syn dihydroxylation. And in this case, we're going to take an alkene and subject it to dihydroxylation conditions. And I'll show you what goes over the arrow in a second. But what happens is we're going to add OHs to both carbons of the double bond in a syn fashion, meaning they end up on the same side. So here would be the product. Because of symmetry here, the OHs out are equivalent to the product where the OHs are back. There's a few different ways to accomplish this with different sets of reagents. One way is potassium permanganate with base and water. Another way is by adding osmium tetraoxide, followed by, in a second step, a reducing agent and water. The problem with this set of conditions, though, is this would require, for every 1 mole of alkene, 1 mole of osmium tetraoxide, which is a very expensive and toxic reagent. So we really don't want to do that. So the most common and best method for this uses a catalytic amount of osmium plus a reagent known as NMO and water. And I'll explain what the NMO is in just a bit. So I wanted to give you a few different reagents just for completeness, but anytime you see me use this reaction, I'll use these conditions right here. So I'm not going to put any of these other reagents on the exam. So our preferred set of conditions for this is the osmium tetraoxide and a catalytic amount, NMO, and water. So let's look at kind of the basic mechanism for this, and then explain how this catalytic version works. Here's our double bond and the osmium tetraoxide, and it's kind of an interesting structure with so many bonds to the osmium. And this first step is an alkene addition, similar to what we've been doing. We're adding something across the double bond. What we're doing is we're adding 2 oxygens. And the way we do that, the pi bond will attack 1 oxygen. That'll push electrons to the osmium. That will push one of these pi bonds over to the carbon of the double bond. The resulting product has both oxygens added from the same side, either the front or the back, and this is called an osmate ester. From there, the water adds and cleaves the osmium-oxygen bonds. So it ends up giving a proton from the water to these oxygens, and then the OH from water add to the osmium. So in the end here, you get our Syn diol, and our byproduct has 2 OH groups on the osmium. So what the NMO is, it's called a co-oxidant, and the NMO actually oxidizes this product back to the osmium tetraoxide. Because this is a reduced form of osmium because we only have 1 bond to the oxygen. So the NMO reoxidizes those bonds to give us the osmium tetraoxide, which can then dihydroxylate another molecule of the alkene. Just to give you an idea of what the NMO looks like, it's called N-methylmorpholine N oxide. It's kind of an interesting structure. Like this.